Howdy everyone, and welcome to our Chapter 7 example problems. This chapter is all about periodic trends, so there's not really a ton of math, which is nice. It's more, are you understanding where you are in the periodic table and how things, properties of the atoms change as you move left to right, top to bottom, or some mixture of the two. So a couple quick examples. It's very common to get problems asking you to put atoms or ions in order from largest to smallest or smallest to largest. So first off, always make sure you know which way you're going. In this case, we want the largest first and then the smallest. The largest, when we follow our trends, these will be at the bottom of the table because they'll have more shells of electrons which get farther and farther away. Each shell spreads out. And then they'll also be on the left of the periodic table because that's where Z effective is the lowest. You have the fewest number of protons pulling those electrons in. So bottom left will always be the largest. That means the smallest will always be at the top right. Oops, right, the T comes second. And so for sometimes it might just be top to bottom, sometimes it might just be left to right, sometimes it's a combination. But if you always remember these two, then you'll be able to handle any of these problems. So when we look at these, we say, okay, potassium, lithium, cesium, they're all in group 1A. They're all in that far left column, the alkali metals. So since they're in the same column, we only care about top to bottom. The largest will be at the bottom, and that's cesium. So cesium will be the largest. Let me put largest over here so we know which way these answers are going. If you ever get a free response type question, it's always nice to label which way you're going. So even if you're opposite what they particularly ask for, if you've labeled your order, sometimes your grader will let you have it. So cesium's at the bottom, so it's largest. Then comes potassium in the middle, and then lithium's near the top of that chart. It's the top of those three, so that'll be the smallest. Next up, we have lead, tin, and silicon. Again, these are in the same column. They're all in group 4A. So again, whichever one's closest to the bottom will be largest. That's lead. The next one up will be in the middle. Well, that's tin. And then the one closest to the top will be the smallest. That's silicon. So this one was already in the right order, but hey, what are you going to do? Now we have fluorine, oxygen, nitrogen. Now these ones are all in the second row. They're left to right. So here we care about, the largest will be the ones farthest to the left because they have the fewest protons. The smallest ones will be farthest to the right. So the largest one farthest to the left is nitrogen. Then comes oxygen. Then comes fluorine because that's farthest to the right. So if you just, again, apply these two principles, you can get any of these problems done pretty easily. The next bit in this chapter talks a lot about ionization energy and electron affinity. And so this one's a common type where it's just say which one's going to be the smaller first ionization energy. Well, the key trick here is that the smallest energy is always with the largest atom, right? So they go together. The larger your atom, the smaller the ionization energy, easier to pull the electron away. If you have a very small atom, then it will have a higher ionization energy. It'll be harder to pull that electron away. So then we just apply what we did on the last one. The larger the atom will be farther to the bottom and farther to the left. So if we look at these two, chlorine versus argon, chlorine is to the left of argon. It's only got 17 protons versus argon's 18. So chlorine won't be pulling them as hard. So chlorine will be the smaller ionization energy, and that means argon will be larger. When we look at beryllium versus calcium, these are both in column 2A, so now we're looking at top versus bottom. Calcium will be the largest atom. That means calcium will have the smaller, so that was the smallest, but smaller. I'll fix that in post, no I won't. Smaller ionization energy. There is no editing on these videos. Alright, but there you go, that's how you can do these. Just the larger the atom, the smaller the ionization energy. And so if you're ever given 3 or 4 atoms to look at, you do what we did in the last one. Just start with the bottom left for the largest, work your way to the top right for the smallest atom, and then apply how it works with ionization energy. All right, now the last one here, there's, I think, an example problem in the chapter, but they don't have one in the end of chapter problems. But problems like this do show up on exams. I've even seen stuff like this on AP exams and ACS exams. So I do want you to be familiar with this type of problem. I often give a problem like this as part of the lab quizzes. So this is, we've got an unknown element. They list off a whole bunch of ionization energies, and they want you to say which group, which column is this element most likely in. You're not saying which element it is exactly, just saying where is it. And that's based on how far past the noble gases are you. Because we saw in the table of ionization energies in the book, when you try to remove a core electron versus a valence electron, there is a massive jump in the ionization energy. Because say maybe you're going from trying to remove a 3s electron that's farther away to suddenly trying to remove a 2p electron, which is much closer in. Well, now it's much smaller radius, so it'll be a much higher ionization energy. So we look at our numbers to say, where does the jump occur? Where is the massive jump? So we say, okay, we got 400, 550, that doesn't seem too bad. 550 to 800 doesn't seem so bad. 800 to 3,500. Here is our jump. There's the first big number, and then, yeah, to I5 only 4,000 more. So that's the jump from 800 to 3,500. So I3 to I4, that's where the jump occurs. And so we say, okay, that means 3 electrons are removed, and we'll call it easily. It still takes energy, but they're reasonable amounts. But then the 4th electron must be a core electron. That means it must be, that's where the noble gas is. Well, if the 4th one's where the noble gas is, that means our element is 3 electrons past that. It's 3 columns past that. So the first electron gets us to group 1A. The second electron would be, now you're in the second column, group 2A. The third electron means, this is a 3A element, because we can remove 3 electrons without much problem, but the 4th one's where the noble gas is. So that's where you look at that. You say, how many electrons get removed before the jump? That's how many columns in you are. All right, so I hope these problems were helpful to you. There are some other problems in the homework set that have you write equations. I'm not going over those because all of those equations are either exactly in the book. Sometimes they want you to just flip back to those sections and copy the equation exactly, or it's just an analog. The example might be magnesium in column 2A, and they want you to do the reaction for calcium. That means just plug in calcium wherever you see magnesium. They're going to be the same exact reaction type, just change one element for the other. All right, so hopefully that'll help you out, and I will see you all back for Chapter 8. Have a good day.